Okay, so what we're going to do right now is we're going to talk about the introduction to our trig functions. But before we do so, we are going to talk about how to specifically draw out angles in this course from this point on. It's just to stay consistent with how we're getting our solutions to everything. So we can kind of make a comment as to section 1. So we can say that in section 1, we constructed angles by starting from its initial side and we rotated the angle measure to get to its terminal side. So if you recall, we kind of started with the initial side, we rotated whether it was clockwise or counterclockwise, depending on if it was positive or negative angle, and we got to the terminal side, and that was our angle. Now, what we're going to do is, which from this point on, we're commonly going to draw angles in standard form. So we will now discuss angles in standard position. Okay, so let's talk about what, or let's define what it means for an angle to be in standard position. So we would say that an angle is said to be in standard position if its vertex is on the origin and its initial side is along the positive x-axis. Okay, so let's kind of draw this out visually so we see what's happening. But so what we're saying is, to visually describe what this is talking about is this. To draw an angle in standard position, we need to make sure that our vertex is always on the origin, which there it is, and my initial side, which is the side I begin to before I rotate from, is always on the positive x-axis. So that's my initial side. So with that said, and then we'll have a specific angle. So let's pretend we rotate an angle of theta, and this angle is going to tell me exactly where my terminal side is going to go through. So I start from the origin and I draw my terminal side. So this is what it means for an angle to be in standard position. We always start with our initial side on the x-axis, and then we rotate to get to the terminal side and whatever theta is. So we would now say this angle theta is in standard position. Okay, so with that said, let's look at our first example. So for example 1, we're going to say identify the terminal side of the angle alpha by writing an equation for the line. Okay, and so let's start off by drawing out, so this is alpha, there's my terminal side, and this point has coordinates 3, 2. Okay, so we want, so this example is asking us to find the equation of that line that goes through the origin, or writing the equation of this terminal side. Okay, which notice how we notice that this is a line that goes through the origin, which means its y-intercept is 0. If you remember, the easiest way to kind of think about this is y equals mx plus b. That's the equation of a line in slope-intercept form. But what do I know? Since the line goes through the origin, b is 0. So I really need to find the slope, which is the rise over run. So if you think about it, from this point to this point, how much do we go up? We rise 2. And then how much do we move to the right? We move to the right 3. So the slope here is what? Rise over run. So it's 2 over 3. So based off of this, my m is 2 over 3. So the equation of this line becomes y equals to 2 over 3x. Except one thing I want to point out, notice how this is just the half of the line. So this y equals 2/3 x covers more than just the upper half, it also covers the lower half. So to make sure that we only capture the upper half, what do I need to restrict? I need to restrict my x values to specific values. And notice how when I move to the, or when this line goes up, the x values are always positive. So if this went down here, then the x values would be negative. So we would say for x is greater than or equal to 0. So this just guarantees that we're taking the right x values, which this, notice how this line only goes to the right side of the x, it doesn't go to the left side. So there you have it. So it's literally all we did was we found the equation of a line, which I used the idea of slope-intercept form. We could even use point-slope form. It doesn't matter as long as we write the equation of the line. So however you prefer to write the equation of the line, that's up to you. Okay, so let's look at our second example. So for example 2, we would say take the angle alpha from example 1. So once again, we're focusing on this angle alpha. Okay, what for part A, we're going to say find 2 additional points on the terminal side. Okay, and obviously we don't want, and we want to make sure that it's not the origin, because that's not going to be of interest. So we're actually going to try to prove a point here, and this kind of lays back to I believe section 2, where we talked about similar triangles. But if we're saying, look, using this guy, find 2 additional points on the terminal side, well, here's the good news. We already found the equation of this line, didn't we, which is y equals 2/3 x. So using y equals 2/3 x, which is the equation that describes this line, I can just plug in x values here to find the y values, and that'll give me the ordered pair I need to find the points on this line. Now obviously the only x value I don't want to use is what? I don't want to use 3, because when x is 3, y is 2, since this is saying find 2 additional points, so the 3, 2 is already a point on the line, so I'm going to pick other values. So I'm going to, for example, say, well, why don't I pick, and it doesn't matter what we pick, we can choose whatever we want. So I'm going to choose nice numbers. I'm going to say, well, if x equals to 6, if I plug in 6 there, I get y equals to 2/3 times 6, which becomes 4. And I purposely picked 6 because notice how this became a nice number. So the next point is 6, 4, and then the next value I'm going to pick is 9. If x equals 9, then y equals to 2/3 times 9, which ends up being 6. So the next one is 9, 6. So I found 2 more points. So these points are also on that terminal side. Okay, now here's the interesting part. So for part B, we're saying compare the ratios y over x for all points on the terminal side. Okay, now look at what happens here. So if I were to pick all points y over x, so look, let's take this point, 9, 6, which is y over x. So what happens if I take y over x, which would be 6 over 9, which is 2/3. Okay, now let's take 6, 4. Let's do y over x, which is what? 4 over 6, which that's also 2/3. And then if you look at the original point we had, which was 3, 2, if I take y over x, what do I get? I get 2/3. Now notice how all of these points, when I took the y over x, I got the same ratio. Okay, now is that of a surprise? It's not, right? Because what is it that we're noticing that all of these are in proportion? We're being told that, hey, you're dealing with similar triangles. So technically speaking, here's what's happening. If I redraw that picture from example 1, we kind of did this. This was the 3, 2. I'm making a right triangle. And then if I take the 6, 4, I make another right triangle. What do you notice about these two triangles? These angles are the same. This small triangle and this big triangle, they actually share that angle, so that angle is the same as itself. So, and these angles are matching up. So in fact, these triangles are similar. And what you're going to notice in trigonometry, whenever we draw angles in standard position and we create triangles, regardless of which triangle we create, our triangles are always going to be similar. So when we take ratios, they're going to be the same. So it's kind of like a nice result we get. So is it surprising that we got the same ratios for these? Of course not, because we're dealing with similar triangles. Okay, so it's kind of like if you make right triangles, you get similar triangles out of it. Okay, so now let's move on to defining what trigonometric functions are of any angle. Okay, so now what we're going to do is we're going to basically define trigonometric functions. So given any point, and notice how the key word is it's any point. So to kind of go back to last problem, well, no matter which point we pick, the ratios stay the same. So on the terminal side of angle theta in standard position with r as square root of x squared plus y squared, and I'll explain to you where this is coming from, where r is greater than 0, and we're being told that r is always a positive number, which is the distance. And the reason why r is always positive is because it's the distance from the origin to x, y. The 6 trigonometric functions of theta are the following. Sine of theta is equal to y over r. Cosine of theta is equal to x over r. Tangent of theta is equal to y over x. And then we have the reciprocals, and cosecant of theta is equal to r over y. Secant of theta is equal to r over x. Cotangent of theta is equal to x over y. So these are the definitions of our trig functions, okay? So you probably at some point heard about these, especially for sine, cosine, tangent. You've probably heard of the statement SOHCAHTOA, where it's like a kind of a quick way of remembering how sine is defined. Sine by definition is what? Opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, which So let's kind of make sense of where this y over r, x over r, y over x, and all these are coming from. And cosecant, secant, and cotangent, they're literally the reciprocals of sine, cosine, and tangent, which, what does that mean? The y and the r have been flipped here. That's all they are. So let's make sense of this, because you definitely want to remember sine as y over r rather than opposite over hypotenuse for the most part. So if I were to draw a picture, let's kind of draw this out. Let's draw our angle in standard position, because look, for trig functions to be valid, our angle has to be in standard position. So from this point on, draw everything in standard position. If this is theta, let's pretend that this is the point on the terminal side I pick. So if I draw my right triangle, what do you notice? The distance, or the length of this side of the right triangle is what? It's that length, which that's, if you think about it, that's just the x value that I travel from here to here to get to that point. So that's x. And then this distance is what? Is the distance I travel from the x-axis to that point, which is how much I move in the y direction, which is y. So notice how this x is basically that x, this y is that y. And what's r? Or how would I find this? If you think about it, if I use the Pythagorean theorem, what do I get? I get, if I call this r, for instance, r, what would this be? It would be x squared plus y squared equals to r squared. And then so if I solve for r, I get that, square root of x squared plus y squared. So literally, the reason why r is defined as that is because we have a right triangle, and so we're using the Pythagorean theorem. So now look at this. Let's see how this y over r comes about. If we think back to earlier on when we learned that sine was by definition opposite over hypotenuse, see, from this angle's perspective, what's the opposite side? It's that, right? It's opposite over hypotenuse. And notice how this is the hypotenuse of the right triangle, so it'll be y over r, and notice how that's that. Cosine of theta would be what? Adjacent, which would be x over r. Tangent would be opposite over adjacent. And cosecant, secant, and cotangent are just the reciprocals of these guys. So hopefully that makes sense as to why we're getting y over r, x over r, y over x. But this is a much better way of thinking about it, because this y over r, x over r, y over x, it all stays valid no matter which quadrant we land in. Okay? So that's kind of like a visual description as to how we're getting this. But these are the definitions of trig functions that you need to make sure you know. This is pretty much the most important part, or one of the most important things you need to know to be able to be successful in trigonometry. Okay, so let's look at our first example, or our third example. So we could say find the values of the 6 trigonometric functions given the point -5, 5 is on the terminal side of angle theta in standard position. Okay, so for this one, the good news is, see, I could solve this example without drawing any pictures, or just literally drawing this picture out. But I'm going to draw a picture anyway, just so we see it. So here's what we know. We have an angle in standard position. So whatever theta is, we know its initial side starts from here. And the point that my terminal side goes through is what? -5, 5, which is right there. So we know that my terminal side goes through that point, which this is my angle theta. But if you think about it, how we just defined sine, cosine, and tangent, which is these guys, I just need pretty much my x, y, and r. So notice how the x and the y I pretty much already have, because that's the x, that's the y. The points are given. Now, how do I find r? Well, I would need to use the Pythagorean theorem, which, if you think about it, we have -5, 5, and we just need to find r. Or in other words, it's just r is the square root of -5 squared plus 5 squared, which becomes square root of 50, and that becomes 5 rad 2, I believe. Okay, so r is 5 rad 2. So now that we have everything we need, we can just answer this question, because what would sine of theta be? Sine of theta is y over r, so y is 5. So it'll be 5 over 5 rad 2, which the 5's cancel out. That becomes 1 over rad 2. Now to rationalize this, I'm just going to multiply top and bottom by rad 2 to rationalize it, and I get rad 2 over 2. So what would cosine of theta be? It'll be x negative, so my x is negative 5, right? If you think about it, maybe I should write it off to the side because that's important. X is negative 5, y is 5, r is 5 rad 2. So that's kind of, these are the informations I need to answer this. So cosine of theta is what? It's x over r. So x is negative 5, r is 5 rad 2, and they cancel out, the 5's do, and I get negative 1 over rad 2. Once again, to rationalize this, I multiply top and bottom by rad 2, and I get negative rad 2 over 2. Okay, so let's move on to the next one. What would tangent of theta be? Tangent of theta is just literally y over x. So what's y? Y is 5 divided by negative 5. So 5 divided by negative 5 is negative 1. Okay, so now we also need to find the reciprocals of these guys. So if sine of theta was y over r, cosecant of theta would be r over y. And what's r? We said r was 5 rad 2 over 5, which is rad 2. So let me actually, and then what else do we have? We have secant of theta, which is, I gotta make sure you could see this. Secant of theta is what? R over x, and we know that r is 5 rad 2. X is negative 5, which once again the 5's cancel out, and I'm left with rad 2 over negative 1, which is just negative rad 2. And then lastly, we have cotangent of theta, which is x over y. So x was negative 5 over 5, which is negative 1. Okay, so just so you know, just to kind of recap, what I did here was I found x, y, and r, and then I used my definition of my trig functions, how they were defined to find the exact values. So just keep in mind that as long as your angle is in standard position, these rules, this definition applies. Okay, so let's move on to our next example, which is example 4. So this says that the terminal side of the line y equals to negative 1/2 x is in quadrant 2, okay, is in quadrant 2. Find the value of sine of theta and cosine of theta. Okay, so anytime you're being given information like this and you're asked to find sine of theta and cosine of theta, the key here is what? We need x, y, and r. Okay, and in fact, and we can find x, y, and r as long as we have any point on the terminal side. Okay, so here's the key. I'm going to draw, see this equation of this line, y equals negative 1/2 x. That's the equation of my line that we have. And if I were to graph it, and we're told that lands in quadrant 2. So if you remember your quadrants, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. And so if my slope is negative 1/2 x, what does that mean? The slope would mean what's the negative? It's rise over run. So I can go up 1 and to the left 2, which would give me the negative 1/2. So it's kind of like, if I were to draw this out, the whole line is this negative 1/2 x. But why did I only take the upper part? It's because I'm being told it's in quadrant 2. So we know that the equation of that line is what? Negative 1/2 x. Now I need to find any point on this line. And notice how I already found the point, didn't I? Because I used the idea of the slope, where I went up 1 and 2 to the left, which is, see, 1 over negative 2, that's negative 1/2. So since this is a point on the terminal side, I could already use that. Now, for if you want to kind of check this out, you can try any other point. Like you could plug in x equals negative 4 in here and see what the y value would be, and I promise you'd get the same answers. But the coordinates of that point are literally negative 2, comma 1. So with that said, now I have x, y. So x is negative 2, y is 1. Now to find r, I'm just going to use the Pythagorean Theorem, which is this equation. So r is, and remember, r is always positive. We never ever will have r to be negative. What would that be? 4 plus 1, which is rad 5. Okay, so now I could answer this question, right? Because what is it that we want? We want to find sine of theta. So sine of theta is going to be what? Y over r. So it'll be 1 over rad 5. And we want to rationalize this. So multiply top and bottom by rad 5. And we get rad 5 over 5. And then cosine of theta is x over r. So rx was negative 2. So negative 2 over rad 5. You multiply top and bottom by rad 5 to rationalize this. And we get negative 2 rad 5 over 5. And there you have it. Okay, so notice how the important part is whenever we're asked to find exact values of sine and cosine or any trig function, we need to identify x, y, and r. Okay, so the next thing I want to talk about is notice how for our trig functions, sometimes we get negative exact values, sometimes we get positive. And that simply depends on which quadrant our terminal side lands on. So our next key here, or our next thing we're going to talk about, are the signs of trigonometric functions. So the question is going to be, well, how do I know if a trig function is going to be positive or negative? And actually, it's not that difficult. We're going to use the definitions. So what we would say is the following. So if we start off with, we can say that trig functions may take on positive or negative values depending on which quadrant an angle's terminal side lands in. So we can now say, look, we know that. So notice r is always positive. So if r is always positive, what does that mean? If you think about it, why am I talking about r? Because my trig functions depend on what? X, y, and r. So since r is always positive, then the only parts that could make a trig function negative are the x and y values. So in other words, x and y of trig functions determine the sign. Okay, so that's kind of what we're going with. So with that said, we're gonna kind of the way I think about it is I think about this visually, and that's the one beauty of trigonometry. We could always do things visually. So let's determine the signs. Let's figure out, hey, when is cosine positive, when is it negative, and so on. So let's draw a coordinate plane. So if I start off with my coordinate plane, we have quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay, so notice how if I pick, so if I'm in quadrant 1, if I pick any point in quadrant 1, notice how I only care about the signs. In quadrant 1, what are the signs of my x and y values? They're both positive, right? Because if I'm here, my x is positive and so is my y. So look at what happens. In quadrant 1, what do we notice? Cosine is what? X over r. X is positive, r is positive. So that means cosine is positive because a positive divided by a positive is positive. How about sine? Sine of theta is y over r. So if y is positive, r is positive, and if I divide them, it's still positive. Tangent is y over x, and so positive divided by positive, that means tangent's also positive. So in other words, cosine, sine, tangent, and of course they're reciprocals even, right? Because if you take a reciprocal, that's not going to change anything. So cosecant, secant, and cotangent are all positive. So you're going to get a positive value. Okay? Now, what if I'm in quadrant 2? What do you notice? My x value is negative, my y value is positive. Okay? So notice how in quadrant 2, let's see how this works. In quadrant 2, what's sine? Sine is y over r, so y is positive and r is positive. So sine is positive, and obviously if sine is positive, so is its reciprocal, cosecant. How about cosine? Cosine is what? X over r. Now look, x is negative divided by r is positive. So negative divided by positive is negative. So cosine, and obviously its reciprocal, which is going to be secant. So these guys are positive, these guys are negative, and then how about tangent? Tangent is y over x, positive divided by negative, and tangent is negative, and so is cotangent. So what is it that we notice in quadrant 2? Only sine and cosecant are positive. Okay? How about quadrant 3? X is negative, y is negative. So let's see what happens here. In quadrant 3, we would see that, let's think about sine and cosecant. Sine is y over r, so y is negative, r is negative, so negative divided by negative, it's negative. And so is its reciprocal, cosecant. How about cosine and secant? Cosine is x over r, so x is negative, r is positive, so negative divided by positive is still negative, so cosecant will also be negative. How about tangent? Y over x, so negative divided by negative is positive. So we notice that tangent and cotangent are positive. Okay, and then the last one, which is quadrant 4, if I pick a point in here, what do I notice? My x is positive, y is negative, so let me write it here. In quadrant 4, we have what? Sine and cosecant. So sine is what? Y over r, so y is negative, r is positive, so negative divided by positive, this is negative. How about cosine and secant? Cosine is x over r, so positive divided by positive is positive. And then we have tangent and cotangent, which, what do you notice? Y over x, negative divided by positive is negative, and so that be. Okay, so now there is actually a shorthand way of remembering this. I don't know if you've ever heard of this. If you start with the fourth quadrant and you write cast, C-A-S-T, this tells you which trig functions are positive in which quadrant. So in quadrant 1, they're all positive. In quadrant 2, only sine and its reciprocal obviously is positive, the rest are negative. Quadrant 3, only tangent is positive, and cotangent is, of course, and the rest are negative. And in quadrant 4, only cosine and secant are positive and the rest are negative. But to me, I like to think of it this way in terms of x, y, and r. Okay, so however is convenient, you could work that way. So let's look at our next example. So for example 5, we're going to say determine which quadrant the terminal side of an angle in standard position lands in if a sine of alpha is positive and tangent of alpha is negative. Okay, so this one, so notice the only information that we're being given is what? Sine is positive and tangent is negative. So the way I think about this is I kind of draw these out separately, okay? And then we need both conditions to be satisfied. So if I look at sine of alpha as greater than 0 means positive, right? So if you think about it, which quadrants are or which quadrant is sine positive in? Well, if you think about it, sine is y over r. So r is always positive. So whenever y is positive, obviously sine is going to be positive. So y is positive in which quadrant? Quadrant 1 and quadrant 2. Now in quadrants 3 and 4 my y values are negative, so that can't work. So sine is greater than 0 in only these two quadrants. Now we come down to this guy now. Tangent of alpha is less than 0, which means it's negative. Where is tangent negative? Well, tangent is y over x. So where is it where y and x, when I divide them I get negative? In quadrant 2 I believe, what is it? X is negative, y is positive, so positive divided by negative. In quadrant 2 tangent is negative. Quadrant 3 tangent's positive, if you remember, because they're both y's and x's are both negative, and it's quadrant 4. So if you compare these two pictures, where's the only quadrant where they overlap? Quadrant 2. Okay, so the answer here is quadrant 2. So for part B, I would recommend that you guys pause the video and try it out on your own, and then play it and then see if your answer is consistent with mine. So the next one is saying what? Cosine of beta is negative and cotangent of beta is positive. So we're doing the same thing here, right? So we draw a picture here. Where is cosine of beta negative, or where is cosine negative? In quadrant 1 it's positive, quadrant 2 it's negative, quadrant 3 it's negative, quadrant 4 cosine is positive. Now let's compare it with cotangent. Where's cotangent positive? Quadrant 1 is positive, so we'll take quadrant 1. Quadrant 2 it's negative, so we don't want that because remember this is greater than 0. Quadrant 3 it's positive because x's and y's are both negative, and when you divide them you get positive. And quadrant 4 it's negative, I don't want it. So now when I compare them, the quadrant that both of them agree on is quadrant 3. So the answer here is quadrant 3. Okay? So let's move on to one more example, and then we'll wrap up this section with one last type of angles. So given sine of theta is equal to 5 over 13 and cosine of theta is less than 0, find the values of the other trig ratios. Okay, so here's what we know. We're given that sine of theta is 5 over 13. And by the way, since we know sine of theta is 5 over 13, we also get cosecant of theta for free, because cosecant is just a reciprocal of that, so it'll be 13 over 5. However, what I need to figure out now is to find the other trig ratios like cosine, secant, tangent, and cotangent. I need x, y, and r. So if you look at this is giving us some information, because if you remember by definition, what's sine? Y over r. So by looking at this, we know that sine is y over r, so y must be 5, r must be 13, and now we need to find x. So to find x, we have that formula, if you remember, r equals to square root of x squared plus y squared. So here's what I know. 13 equals to square root of x squared plus 5 squared. So this becomes 13 equals to square root of x squared plus 25, and then if I square both sides, I get 169 equals to x squared plus 25. Subtract 25 from both sides, I get x squared equals to 144. And then if I square root it, I get x equals to plus or minus 12. Now remember, when I square root it, I put the plus or minus 12 because x could be positive or negative. Now, how do I know which one I take? Well, here's where this second fact comes in. We're told that what? Cosine of theta is less than 0, which means cosine is negative. So for cosine to be negative, its x value must be which one? Positive or negative? It must be negative because we want the negative, right? If cosine of theta was greater than 0, then we would take the positive. So that means x is negative 12. Now that I have my x, y, and r, which is the difficult part, I could answer the question. So now comes the easy part. Cosine of theta is, by definition, x over r, so negative 12 over 13. And then its reciprocal, secant of theta, would be 13 over negative 12. And then we have tangent of theta, which is y over x, so it's 5 over negative 12, so it'll be negative 5 over 12. And cotangent of theta is x over y, which would be the reciprocal of this, and that'll be negative 12 over 5. Okay, so notice once again, it just comes down to us knowing our x, y's, and r's. Okay, so the last thing we're going to talk about is something called quadrantal angles, which is probably, in my opinion, these are the easiest angles to work with. Okay, so these are angles in standard position in which the terminal side lies on the x-axis or y-axis. So in other words, let's kind of think about this. What are quadrantal angles? If I draw this angle in standard position, my terminal side either has to land on the x-axis or the y-axis, which here's an example. Notice how, what would this angle be? That would be a 90-degree angle, right? And then what's another possibility? If I draw my angle in standard position, it would be that one, right? So notice how this lands on the x, and my terminal side is on the x-axis, so that would be 180 degrees. So basically, my quadrantal angles are which ones? It's basically your terminal side lands on the x-axis or the y-axis. So if I were to list them out, so we would say some quadrantal angles are even 0 degrees, right? Because 0 would say what? Start from the initial side and don't rotate, which you end up there. So 0 degrees, 90 degrees, 180 degrees, 270 degrees. These are all quadrantal. And then I could even say negative 90 degrees, which would mean rotate this way, right? So these are my angles that are quadrantal, okay? So let's look at our last example. And this will have to do with quadrantal angles. And by the way, quadrantal angles still follow the same rules if we're asked to find the trig functions. We still need x, y, and r. Except, in my opinion, finding the x, y, and r for quadrantals are much, much easier. So evaluate the 6 trig functions of theta equals to 270 degrees. Okay, so in this case now look, we've been given the angle, whereas if you look at the examples before this, we were never given the angle. We were just given kind of like the exact value where we could identify the x, y, and r just by looking at it. So when given an angle and asked to find exact values of trig functions, we will follow these steps. Okay, so I'm going to kind of give you the step by step. So step 1, draw angle in standard position, which that's not difficult, right? Because we have our angle, it's 270 degrees, and that in fact is a quadrantal. But if this is my initial side and it's 270 and it's positive, I'm rotating counterclockwise, 90, 180, 270. So there's my terminal side. So once we draw it, then step 2 would be pick any point on terminal side, which for this one it's much easier, right? So I could pick this point, and since it's up to me at any point, I know that no matter how much I move up or down, my x value is always 0. So I'm going to call this 0, -1. Okay? So then step 3, identify x, y, and r. Well, here's what I know. Based on the point I've picked, it's what? X is 0, y is -1. What would r be? Well, r is just the square root of x squared plus y squared, which is square root of 0 squared plus -1 squared, which ends up being square root of 0 plus 1, which is 1, and the square root of 1 is always 1. So we just noticed that r is also 1. So once we have this, once we have x, y, and r, then we can say step 4 is find the exact values. So to find the exact values, we need just to use the definition. So sine of 200, now I'm going to write sine of 270. I'm not going to put theta anymore because I know what the angle is. Okay, so just keep that in mind. In the previous examples, I would put sine of theta because I didn't know what the angle was. But now that we know what the angle is, we have to put it. So sine of 270 is what? Y over r. So -1 over 1, which is -1. And then we would say that cosecant of 270 degrees is what? R over y. So it's 1 over -1. That's still -1. And then we could say cosine of 270 degrees is x over r. So x is 0 over 1. And 0 divided by 1 is always 0. Secant of 270 degrees is what? R over x, so it's 1 divided by 0, and that's a problem. We can never ever divide by 0. So if you're dividing by 0, that just means this is undefined. So this does not exist for secant. So secant of 270 degrees does not exist. And in fact, anytime we divide by 0, just know that that doesn't exist. And then we have tangent of 270 degrees, which is y over x. So y is -1 over x is 0. Oh, once again, we're dividing by 0, so this is undefined. And lastly, we have cotangent of 270 degrees, which by definition is x over y, which would be 0 divided by -1, and 0 divided by -1, that's fine, that's 0. So, and generally the undefined values, it's natural for us to get it when we have quadrantal angles. And notice how this was a quadrantal angle. Okay, so these are some, this was kind of like an introduction to trigonometry where we got to define the trig functions. We will work with this kind of stuff constantly throughout the semester. So please, once again, if you do have any questions, don't hesitate to ask me and I'll be more than happy to answer them.